All right, so what we're going to do this time around is kind of go backwards. We started off with 3.2 to talk about some matrix operations, right? And we got used to dealing with matrices. Now we're going to go back to 3.1 to talk about something called a linear transformation. But before I do that, I just want to review a couple things about linear independence and dependence, and in terms of span, right? Because those are going to be very much linked to linear transformations. All right, so let's just kind of walk through this just as a review. Suppose you have m vectors in Rn, right? So each one of these guys has n components, right? So I'm going to write them as column vectors as we normally would. And I form a matrix where each of the columns of the matrix corresponds to one of those vectors, right? That's our normal approach. And what we've typically have done to determine if those vectors span Rn or if they're linearly independent, everything rested on putting it into echelon form and noticing if there was a row of zeros and or if every column had a pivot, right? And there were direct consequences, equivalences to whether or not each of those happened. All right, and so let's look at this. The vectors are dependent, right? So one will be able to be written as a linear combination of the others, right? If and only if, so this is an equivalence, there is a column with no pivot, right? Now remember, what that means is that if there is a column with no pivot, there's going to be a free variable. The minute there's a free variable, you have complete control, right, over one of them. And that means you can write one in terms of another, right? So a set of vectors is linearly dependent if and only if the matrix formed using those vectors as a column is such that one of those columns at least has no pivot. All right. And then, of course, they're linearly independent if every column has a pivot, right? It kind of goes hand in hand. All right, and then likewise, those set of m vectors spans Rn if when you put the matrix in echelon form, there is no row of zeros, right? So every row has a pivot. Every row has a leading term that's not zero, right? So there won't span, right? So those vectors will not span Rn if and only if there is at least one row of zeros, okay? So just kind of recalling what those mean because they're going to come up now when we talk about linear transformations. Okay, so now what do I mean? Let's increase the size and hope I remembered. All right, so a linear transformation is a mapping, right? So you're used to dealing with functions, although your functions up to this point either were like f of x equals x squared. If you've taken Calc 3, then perhaps you had f of xy equals sine of x plus e to the y, right? So they took a ordered pair or even an ordered triple to a real number. The difference here is we're mapping vectors to vectors, right? So there is no nice picture, so to speak, that contains both the domain and the range, right? You need at least 4 dimensions to be able to get a picture of what this looks like, right? So we don't rely on understanding a picture in the same sense. Rather, we rely on properties of the mapping. All right, and so for example, let's actually take this. I'm going to rewrite this in column form. I think it's easier to deal with in column form. Oops. All right, so I'm going to write this as T of x1, x2. So I give you a input. So the input now is a column vector with 2 components. And the corresponding output for the first component, you have 3x1 minus x2. And for the second component, you have x1 plus 2x2. Okay. 1 second. I'm going to make sure the mic is working, so hold on. Okay, sorry about that. I just wanted to make sure the microphone was working before I went ahead and recorded the whole video. Okay, so I'm going to write it like this, but I want to also write it in a form for which I'm going to be able to use our matrix properties. And so I'm going to separate this. Remember how we add vectors? You add component-wise, and you can also scalar multiply. And so what I'm going to do is break this up into a sum where I have the x1 guys in one vector and the x2 guys in another, right? So certainly that's true, because if you were to add those, you would add corresponding components, you would get that, right? So I'm just doing this so I can write it a different way. Now notice here, the x1 and the x2 are real numbers and they're common to both components, so I could yank them out, right? So I have an x1 times 3, 1, and a plus an x2 times a negative 1, 2, right? So I can write it in that way. And that's going to be helpful, number one. Number two, another way of writing this is using a matrix times that vector, right? So that's another way of writing it, because if you multiply row times column, you get 3x1 minus x2, that's that guy, and then 1x1 plus 2x2, which is that guy, right? So these are both ways of writing that transformation, and both are going to have utility. All right, I should move that here. All right, so let's first show these two properties, right? So here, in other words, if you apply a linear transformation to a sum of vectors, you can apply the transformation to each of the vectors separately and add them up, right? And then you can yank out scalars, right? So if you think back to Calc 1 and Calc 2, that's what we keep saying, that an operator is linear. It means that, like the limit of a sum is the sum of the limits. The limit of a constant times a function is the constant times the limit of the function. Same thing held for derivative, same thing held for integrals, right? So those are all linear operators or linear transformations, but not from R2 and R2, but in kind of a function space. So this is the same idea. It's just that now we're dealing with vectors. All right, so here, let's actually remember our, let's take any old U1 and U2. So I'm going to say U1 V1 plus U2 V2. Okay, and so here, remember how you add, how you add vectors. This is U1 plus U2 and V1 plus V2. Oh, no, wait a minute, sorry. Change this to a U2. This to be consistent. I'll use the same letter. I'll change the subscripts. Sorry, so all these guys are U1, U2. This is V1, V2. Thought it looked weird. All right, and so then the top component is U1 plus V1, and the second one is U2 plus V2. Okay, now I want to take T of that. Well, this acts like my X1, and this acts like my X2, and so I'm just going to plug them in here, right? Just using the first one. This is 3 times U1 plus V1 minus X2 is this guy. And same way here, T of U2 V2, I'm going to plug in X1, which is U1 plus V1 plus 2 times X2 is U2 plus V2, right? So if I just computed T of that sum, that's what I get. What I want to do to argue this is that I can pull things apart, right? And we kind of seen this in action up here. I'm going to do basically the same thing. I'm just going to clump the U guys together, and then the V guys together. Okay, so let's do that. This is, if I distribute the 3 through here, the negative and the 2, and then combine, I have a 3U1 minus U2 and a U1 plus 2U2, all the U guys together and all the V guys together. And then back here, I have a 3V1 minus V2 and a V1 plus 2V2. Okay. But notice here, this is precisely T of U, right? Remember, U was U1, U2. If I plug in U1 for X1 and U2 for X2, I get those two components. Sorry, these two components. And in the same way here, that is T of V, right? So by just using how you add vectors applying the transformation and then pulling apart the u and the v's, you can show that that works. Okay? And similarly for scalar multiples, this is part A. For scalar multiples, right, if r is any real number, right, this has to work for every real number. And I take t of r times u1, u2, right, that's u. Well, remember how you scalar multiply. You multiply both of the components of u by that r. Well, now plug them in. This is my x1, this is my x2. I'm going to plug them in here. So I get the vector 3ru1 minus ru2 and ru1 plus 2ru2. And notice, an r is common everywhere to both components. I can bring that r out. And what I'm left with is 3u1 minus u2, and then u1 plus 2u2. But this is just t of u. So you get rt of u, right? And so you can pull out constants. Let me get some paper here. You can pull out constants as well, right? So this mapping satisfies both those properties. Great. All right, let's go on to the second one. So B, right? So the question here is, given a vector B, does there always exist a input in the domain for which the t of that is B? In other words, is t of x onto R2? That's another way of saying that. So is t onto R2? Well, if the only way it's going to be onto R2, if you look back here, right, that's like saying that for a B in R2, since this is t of x, right, we call this x, this is t of x by definition. Okay, so for B in R2, does there exist an x in the domain of t such that t of x is B? All right, that's what we're asking. But in terms of this notation, we mean, i.e., does this system, and I'm going to call B B1, B2, does that have a solution? And that has to be for every B. Well, the only way that's going to have a solution for every B, remember, is if there are no zero rows, which that would mean that these vectors span R2. That's what we just reviewed, right? So all we have to do to answer this question about onto-ness of R2, of T, is determine whether or not the matrix used to define that transformation, right, has any zero rows in echelon form. Yeah? So a linear mapping is onto if and only if the matrix used to define that mapping has no zero rows when put into echelon form. All right, let's do this. So let's start 3, -1, 1, 2. To put into echelon form, I need to make a 0 there. So let's take -1/3 of R1, add it to R2 and clunk it into R2. That doesn't change the first row. The second row, you get 0. If I multiply this by -1/3, it's 1/3. Add it to that guy, I get 7/3, right? And that's it, no zero rows. Right, so these guys span R2, and hence the answer to that question is yes. Right? Okay. Number C, or letter C rather, let's look at that guy. If TU is equal to TV, what can be said about U? All right, so now you might recall this from Math 200 if you've taken Math 200. You've seen that if you take any two members of the domain and these guys are equal, if that implies, and we'll put a question mark, that U is equal to V, then the mapping is said to be 1-to-1. So let's walk through this. Right, again, eventually we want a link, just like we had for onto. We would like a link between this property and the matrix A that defines the transformation somehow. All right, well, let's look at it. So let's assume that T of U is equal to T of V, right? Oops, so I'll fold this in half. You can see everything. Okay, so we have our, zoom out a bit, sorry about this. There you go. All right, so there's our mapping T. And what I'm gonna do is I'm gonna use this form this time around. So T of U is equal to, remember U is U1, U2. So T of U1, U2 is U1 times that guy plus U2 times that guy. So U1, 3, 1 plus U2, negative 1, 2, right? That's T of U. We're assuming that that equals T of V, which is that, that's T of V, right? Well, let's actually bring everything to one side. I'm going to bring these guys to the left. And then I'm going to combine them based on what vector, right? So I'll have a U1 minus a V1 times this vector, right? Because they have the same vector in common. I can factor it out. excuse me. And then plus a U2 minus V2 times negative 1, 2. And that's the 0 vector, right? Because I pulled everything to the left. Okay. But notice here, that's a scalar multiple of this vector. That's a scalar multiple of this vector. And that's the 0 vector, right? So remember, this is a linear combination of these guys. If you think back to the definition of linear independence, what we said was that these two vectors will be linearly independent if the only linear combination of those guys that produces the 0 vector are the scalars that are all 0. Okay, so the question here is, you know, if we want this to imply that these vectors U and V have to be the same, right? Then what we have to argue is that that's equal to 0 and that's equal to 0, right? If one of them isn't 0, then U is not equal to B, right? Corresponding components have to be equal. So if we want to argue that this and this both have to be 0, what we're really asking is, are these vectors linearly independent? But remember, that boils down to asking if when you put the matrix in formed using those vectors as the columns, if you put it into echelon form, which we had already done, in echelon form, if every column has a pivot, then the vectors are linearly independent. Remember, a pivot is a leading term, a non-zero leading term. So here is a pivot, there is a pivot. Both columns in that matrix have a pivot. And so, all right, so each column has a pivot. So the columns are linearly independent. But if they're linearly independent, then go back to the definition. The only way this is going to occur, right? So this now comes, the reasoning for this implication is what comes between. The only way this can happen is if those scalars are both 0, right? But notice that that tells you about the components of U and V, right? U1 is equal to V1 and U2 is equal to V2. But that means that the vector U is equal to the vector V because U and V have those components in particular, right? So now good, we have a relationship between the matrix that defines the linear transformation, right? Between that and 1-to-1, right? If this matrix, when reduced to echelon form, is such that every column has a pivot, then that mapping is 1-to-1, and that's an if and only if, right? So which means those properties are going to go into our equivalence that kind of unifying theorem that we've been building all along. Keep that in the back of your head. Okay, so there is the first sort of main example. All right, so let's actually summarize that into a definition. Right, any mapping, and you don't have to go from R2 into R2. You can go from Rm to Rn, and they don't have to be the same dimensions. Such a mapping is a linear transformation if T of u plus v is equal to Tu plus Tv, and you can yank out scalars, right? And that's true for every u and v in Rm and for every scalar R. All right. And then, you know, just in terms of a picture, and this picture doesn't really do much, but I'm going to picture the domain over here as Rm, and the codomain is Rn. And here, we take an X and you apply T to it, right, to get B. So it's just a mapping diagram, right? It just takes any X to a member B. This B is equal to T of X. It's called the image under T, right? So this is just terminology. And the X back here is the pre-image of B, right? It's the vector that when you take T of it gives you B back. If you take T of everybody in Rm, you don't have to get Rn, right? It doesn't have to be onto, but rather this space here is a subset. If I take the image T of Rm, that's a set. This is a set of all possible vectors in Rn that are produced by taking T of somebody in Rm, right? If this is equal to all of Rn, we'll call the mapping onto. Okay, so just some terminology. Let's take a look at this guy, right? So let's determine, if I gave you a mapping, let's determine if it is a linear transformation. So this time, and again, I'm going to look at these in terms of columns. So T of x1, x2 is equal to x1 minus x2, and then x1 times x2. All right. So let's actually take a look. The first thing here, if you look back at our original example back here, you can kind of tell that the way this was produced is by looking at this directly and yanking off coefficients. So assuming you have this is nice and simplified, there's 1x1 and 1x2 in each of those being added or subtracted. Same thing here, right? If there's more than one each time, you combine the like terms and get it down to a simplified form like that. All these coefficients all these entries in this matrix are the coefficients of the x1 and x2 back there, right? And so that begs the question, if I give you a mapping like this, well, if you're trying to form a matrix A in this case, right, A will be a 2 by 2 technically, because there are 2 rows and 2 columns, 2 rows and 2 outputs, right, because these are two the same. The first guy is easy, 1 and -1. The problem is here, right, that's a product. And so you only have one single number there technically, right? It's not a sum or difference. And so the question is, well, what on earth would I put there? Right? If there's that hesitance, that suggests that the mapping probably is not a linear transformation. It's not a proof, right? Because we not just not be insightful enough to do it. But to prove it, we have to show that one of these properties fails. All right, so let's take just a very easy vector, u equals 1, 1. And let's take a scalar, let's say 2. Let's look at t. And sometimes this just takes some tinkering to work with, but don't try to have just vectors at random. Try easy ones. All right. Let's look at 2u, right? So t of 2u would be t of 2, 2, right? Because I'm taking u to be 1, 1 and r to be 2. Here, the x1 and the x2 are the same. And so I get 2 minus 2, which is 0, 2 times 2, which is 4. Right, so t of 2 times u is the vector 0 times 4. Now, if it were to be a linear transformation, this would have to produce the same thing as 2 times t of u. Well, that's 2 times t of 1, 1. T of 1, 1, well, you still get a 0 for the first component. 1 times 1 here is 1. But if I multiply that vector through by 2, I get 0, 2, not 0, 4. Right, so those are not equal. And so, since this does not hold for every real number r, we conclude it's not a linear transformation. Right, so since property 2 fails for some r, it doesn't have to fail for anything but 1. The minute it fails for 1, whole thing's not going to work. Right? But if you, now that's different than saying, well, I showed it worked for 4 or 5 of them, then it must be. No, it has to work for all of them, right? So showing it is a linear transformation is harder than showing one's not, right? You simply need to produce a single case for which it fails to prove it's not a linear transformation. So since property 2 fails for some r, T is not a linear transformation. All right, and so anything like this, right? So these guys here, if you have those in the components or whatnot, they are not linear, right? They produce, there are cases for which these properties do not hold, right? All right, so now, hold this down, oops. All right. So here, the minute we know that those two hold, then technically we can argue that that works. Let's actually show a little bit of that, right? So I just want to, if you would have to prove the whole thing by induction, but I'm not worried about that. Let's just show if I took 2 vectors and 2 scalars, right? So assume T is linear. This is like how you would argue a limit of a constant or a linear combination was the linear combination of the limits, right? So it's kind of a similar taste to it. Okay, so remember here, you have T of, we'll call U, U1, U2, and V, V1, V2. So we have R1, U1 plus R2, R2, V1. And then R2, U2, I'm sorry, R1, U2 plus R2, V2. Right, so in other words, I'm just distributing the scalar in each of these cases to get this, okay? Well, now I'm going to do the same thing I did before. I'm going to group the U's together, right? So I know that I can take T of, I'm going to pull these apart. So I have an R1, let's see here. Well, actually, hold on. That's going to be kind of silly. Hold on. Forget I said that. Sorry about that. All right. I was going somewhere where I didn't want to go. That happens. Pardon me. Okay. So here, what you can argue is this, right? We know that you can pull apart these guys. Oh, maybe that's what I'm sorry. That's what I was. I didn't want to go to components, right? So here, I'm sorry about that. All right. So here, treat this as a vector, and that is a vector. So this is T of R1U plus T of R2V, right? So we know if T is linear, we know that T of a sum is the sum of the T's. We also know that for a given T, I could yank out scalar multiples. That's what I wanted. So I can pull out the R1 and I can pull out the R2. All right. And so notice here, T of this linear combination where I have R's on each of these guys is equal to the linear combination of the T's. Right? That's what I was trying to go for, not the components. All right. And so in general, what I was going to argue was that if you had a sum of M vectors in here, do I want N or M? Doesn't matter really. M. Okay, so if I have M vectors multiplied by scalars, You could argue inductively, technically. This would be the base step. I would assume I have the property for m vectors, and then you'd argue that you'd have the property for m plus 1. But you can show that you can break this up into the sum of m pieces. Okay. Now, why is this important? This is important because if these vectors here, if u1 through um span Rn, right? So if these guys span Rn, that means that everybody in Rn can be written in this way, right? So no matter what vector you give me in Rn, it can be written like that. But then the minute that happens, everybody in the codomain of T can be written like this, right? So in other words, I'm using always these vectors. I'm just changing the scalars for the input. But since I can rewrite T of that guy as this sum, notice that these are always the same. I'm just changing those scalars in accordance, right? So what that says is that you can describe the range of a linear transformation just using those m vectors if we know u1 through um span the domain. All right, that's a key point. So that's what I was making here. All right, so let's look at this example. So I want to compute that using the property we just said held. Well, we know that I can break up the sum of those guys and I could yank out the scalars, right? So by that property, this is just 2 times T of u minus 3 times T of v. But I already know what T of u is, right? I'm going to write this in column form. T of u is 4, 3, and T of v is 1, 2. I know I can scalar multiply in, right? So I get 8, 6, same way, minus 3, 6. And then I can compute the difference by subtracting components. Okay, so I get 5, 0. So knowing just those two, I was able to compute T of that linear combination. All right. Now we've spoken about onto and surjective. So onto, another word for onto is surjective. Another word for one-to-one is injective. So again, just terminology. Onto means that the range is equal to all of Rn. So in other words, give me anybody in Rn, I can find a member of the domain for which T of that member is equal to that vector. All right. And so here, what we argued in our example, right, is that T is onto if and only if the columns span Rn. All right. So if you put the matrix in echelon form, there are no 0 rows. So no 0 rows in A when in echelon form. We illustrated that with our example. And then same way, T is 1-to-1 if this holds for every u and v in the domain, right? So give me any u and v you want. If T of u is equal to T of v, then if that implies u is equal to v, T is 1-to-1. And we know that that happens, right, if and only if the columns are linearly independent. Again, go back to our first example to see the reasoning why that connection holds. All right. And so in particular there, every column of A in echelon form has a pivot, right? So remember, that's just kind of another link, right? The way you show that is by appealing to the matrix that's used to define the transformation, and show that in echelon form, every column has a pivot. In particular here is this case when, remember, your mapping is going from Rm into Rn. And so here, if you have the only way that there's not going to be a row of zeros, right, is if the m is bigger than or equal to n, right? So if m if the domain has a smaller dimension than the range, right? And we're going to illustrate this with some examples. But if that happens, then T cannot be onto. So it's a very simple way to actually conclude a mapping can't be onto. It doesn't tell you that it is onto. It just says that if this happens, there's no way it can be onto, right? So if you have a mapping, just remember what the M and the N refer to, right? M comes before N, and so it's for the first guy, for the domain, right? So if the domain space has a smaller dimension than the range, right, it cannot be onto. If it's bigger than or equal to N, you have absolutely no idea. You have to actually test it out and see. And then likewise here, if it's the reverse, it can't be 1 to 1. All right, so that's just kind of a sufficient condition for it not being onto or 1 to 1. Okay, but that's all it is. It doesn't tell you anything about when it is. All right, let's look at these guys. We know that all you have to do if I give you this transformation is determine if the columns are, if they span Rn or if they are linearly independent. And that comes down to putting it in echelon form and seeing if there are rows of zeros or if there are columns without pivots. So let's put it in echelon form, right? To do that, we need to put a 0 there, right? And so all I'm going to do is subtract R3 minus R1 and put that into R3. If I do that, it keeps R1 and R2 the same, but the third row becomes 0, -1, 4, 3. And then I want to put a 0 there. So all I'm going to do is add R2 and R3 and put that into R3. Okay. And so again, that keeps the first 2 rows unchanged. The bottom row now becomes 0, 0, 7, and 4. All right. So notice there are no zeros. I'm going to put this like this. There are no 0 rows. Right, that's in echelon form. Has to be in echelon form, otherwise you can't make any conclusion. There are no 0 rows, and so it's onto. T is onto, right? So the linear transformation defined by T of x is equal to AX. That's what I mean here by this, right? So this mapping here, using that matrix, is onto. And furthermore, if you look at the pivots, this guy has, these are the pivots. This column has no pivot, right? And so there exists a column without a pivot. And so the vectors are linearly dependent, which means T is not 1 to 1. All right. Now notice there also we could have concluded directly, right? So we made this observation, right? The M here is the 4, that's 3. So since that was true, we knew it was not 1 to 1. So you could use that directly, but the reasoning that works is because that'll always lead to at least one column having a pivot, right? So they're very much, one's just an observation based on the other. But if you happen to remember this and do it correctly, you don't have to go through that reasoning each time. But this is actually healthy to do. All right, note here, well, we know it's not going to be onto, right? Because the M is less than the N, right? But that means eventually we expect there to be a row of zeros when you put this in echelon form. Well, let's do that. So if I put into echelon form, okay, then I'm going to, I want a 0 there. I'm going to take 1/3, -1/3 of R1 and add it to R2 and replace R2 by it. So I get 1, -1, 3, 2 stays this, oh no, 3, 2 doesn't stay the same. That R2 becomes 0 and that becomes 5 rather. And then you have 0, 4 there, right? Still not echelon form. I need to have a 0 here, right? And so there you go, right? I'm going to take -4/5 of R2, add it to R3 and replace R3 by it. And lo and behold, that produces your 0 row, right? Which we knew had to happen. So it's not, T is not onto. Remember, T of x is equal to AX. This is the matrix I'm using. So that mapping is not onto. However, every column has a pivot, right? So if every column has a pivot, we know the vectors, the column vectors, are linearly independent. Whoops. That's sloppy. Right, so the column vectors are linearly independent. And that means that T is 1 to 1. Okay. All right, and then the final one there is just one more. Oops, this guy here. Now, look, we have R3 into R3, so we can't use that information about if M is less than or bigger than N, then one or the other doesn't hold, because they're the same. So we can't make any conclusion here. We have no choice but to put this into echelon form, right? And so let's do that. I want to put a 0 here. So I'm going to multiply R1 by negative 4, add it to R3, and replace R3 by it. And then that gives me, oops, rows 1 and 2 stay the same. That gives me the bottom row as 0, -3, -6. All right, and then I want to put a 0 here, which means I'm going to multiply R2 by 3 and add it to R3 and replace R3 by it. So those two remain the same, but if I do that, I get a 0 row. Right, the minute I have a 0 row, that implies that T is not onto. Okay, and then furthermore, here are the pivots, right? There is a column without a pivot, right? So there is a column with no pivot, and so T is not 1 to 1 either. Okay, so you'll have mappings from R3 into R3 that are onto but not 1 to 1, 1 to 1 but not onto, both or neither, right? All of those possibilities are possible. All those scenarios are possible when those dimensions are the same. So you have to put it into echelon form. Okay, this was the unifying theorem that we had been building, right? So we knew that if you're going from Rn into Rn, right? So in other words, if you had a square matrix, then we knew already that those were the same. Those were equivalent statements. We built that last time. But now, since we have that strong connection between the linear transformation and this matrix A, we can put these into the mix, right? T was onto if and only if the vectors were spanned Rn, and T was 1 to 1 if the columns were linearly independent. And so since each one of those is equivalent to one of these guys, and these are already equivalent, we know that all 5 are equivalent. Okay, so that's kind of nice. We're building this unifying theorem that involves basically square matrices. All right. So here, it's kind of interesting if you study the geometry of these transformations. It's kind of interesting to kind of see what they do pictorially, right? And so what we're going to do here, we know, for instance, that 1, 0, and 0, 1 span R2, right? So for instance here, if I look at T of, let's call it R1 times 1, 0 plus R2, 0, 1, we already know that's R1 of T1, 0 plus R2 of T of 0, 1. We know that from our general property. And since these two guys we know they span R2, right? So these linear combinations produce all of R2. So these guys are already known. They span R2. Then we know that these are any member of the range of T can be written in this form. And so in other words, all I have to do is know what T of 1, 0 and T of 0, 1 are based on the matrix A that I'm given, and I could actually compute everything in the range in terms of those guys. So what I want to do here, right? Remember, if you take these guys here, if you take any member where any point in the plane for which the x1 and the x2 are between 0 and 1, each time you are looking at the unit square. Right, so I'm only interested in what happens to these guys under t. In other words, if I apply t to these guys, which are scalar multiples of those, I want to see what happens. Notice that these vectors are positioned right there on the axes, right? All right. So let's do this. Let's compute t of 0, 1 and t of 1, 0. And I want to then show geometrically each time what the image looks like, right? So I'm just going to look, I'm going to map where does that vector go, where does that vector go, right? So t of 0, 1 is this guy. Here, remember, t of x is equal to this. So, excuse me. So t of 0, 1, I'm going to plug in 0, 1. Remember, this is ax. I'm going to multiply those guys. So t of 0, 1 is this product. That's the vector 0, 2. All right. And so the image of 0, 1 is now 0, 2. So it gained. And same way here, t of 1, 0 is a times 1, 0, which is 3, 0. All right, so this is 1, 0. T of it is 3, 0. Right, and if I take any scalar thereof, it's going to shrink each one the same amount. And so notice that you get this sort of dilation of this square. It gets larger because of these numbers in here are larger. If these were fractions, these would be fractions here, it would shrink the vectors. And so we call this sort of diagonal matrix here, where they're both positive, a dilation, geometrically at least. All right. If you do exactly the same thing here, t of 0, 1 is this matrix times 0, 1, right? But that's equal to 0, negative 1. And t of 1, 0 is just this matrix times 1, 0. That's equal to 1, 0. All right, so what does that say? Oh, hold on 1 second. I have to plug in my computer.